Let's get started. A lot of commercials, a lot of goals for today. And tomorrow or Thursday, we will not be formally meeting in class. I think this area will be occupied, maybe, or you might not be able to get down to this room. Maybe you don't want to be in this room once you get down here. So we'll avoid that, and I'll try to allow a lecture on the D2L site to make up for that missed opportunity. I know that you're anxious to try to find when you might be able to do that. Homework 8 is being turned in, or a few are being turned in. This stack doesn't look quite as tall as some of the others. There's homework 5, 6, and 7 that's being returned. I do have some old exams also that I can return after class, and we'll try to take care of that. Homework 9 will be due in a week. Hopefully that will be made available today on the D2L website. That will be more diode material, which we are going to try to finish up Chapter 10. The final exam is then 2 weeks from that the next Thursday. And it will be at 2 o'clock. You'll need to make sure and set your alarm a little earlier. You'll need to get here at 2 o'clock instead of 3:30 on that particular Thursday afternoon. That should be the 16th of December. Today what I want to talk about is the remaining portions of Chapter 10. And I'm assuming most of you went out and bought your devices or elements to try to build what we were talking about last time with respect to the diode. We'll talk a little bit more about that with current limiting resistors. We'll discuss Zener diodes and what those might produce in terms of their IV or current voltage characteristics. We'll look at some load line analysis, or essentially we have two equations with two unknowns, and we are looking for an intersecting point to see where the operating point will actually be. We'll do a few more examples with ideal diode analysis, and that simply means we start making some of these assumptions. Are these diodes on? Is this one off? Etc. And trying to work forward from that. Then you can use these diodes in various ways. One way to use them is to create rectifiers, which is a way to convert AC or alternating current voltage waveforms into a more direct current or DC type waveform. That's what you can create by putting some of these diodes into certain circuits. You can also make wave shaping circuits, and we'll talk about that if time permits. And those are the topics that we'll be dealing with, mainly the load line analysis and some rectifier examples. That will be homework number 9. That's the topics for homework number 9. We talked last time, I think, we were just finishing with a particular circuit that you were going to use or could be used to turn on a diode, or actually what we might want to think of is now instead of that just being a plain ordinary diode, maybe we want to precede it with a couple of more names and call it a light emitting diode or an LED. And that's what we want to talk about now. For example, this circuit is going to have a current flowing through it if the voltage being applied exceeds the forward voltage V on the diode, which if we're assuming an ideal diode, we might just, to get us started, we might assume that that voltage is 0. and when it's conducting, it's going to be 0 volts dropped across that diode, if that was an ideal. I think that's what we talked about last time. If we had an ideal diode, and remember, this particular configuration is equivalent to something like that. And you can now write, maybe more effectively, your KVL equation when you see the circuit in that form instead of this simple vertical line that now has one of the nodes labeled as 10 volts. That's equivalent to what I've now combined this red and green circuit diagram into. If we had an ideal diode in the forward bias region of operation, and I'm not, hopefully after this homework assignment you know what I'm meaning when I say an ideal diode. It's not going to conduct if the voltage applied or across that diode is negative. So this is our current and this is our voltage curve. This would be an ideal diode, and if it gets positive in voltage, then it can support an unlimited current through that. That's ideal. Obviously, a practical diode cannot support an unlimited amount of current, and it also requires a certain amount of voltage across it to bias it to make it turn on. But with this particular ideal diode characteristic, in that diagram, we can then say, oh, we have 10 volts on the top side of that 2K resistor, which translates into a voltage drop across that 2K, but now the top side or the anode side of that diode is more positive than the cathode side. It is forward biased. It will conduct. Because of that, diode conducting, it now allows, this is now a one-way valve, it now allows current to flow through that diode, and we have 0 volts dropped across it. And if we now write the KVL equation, we're going, let's say, minus 10 volts plus this R, which was 2K, times I, plus V, which was the drop across the diode, and we just assumed that to be 0. We can now use this ideal assumption to gain some insight into the current flowing through that diode. Everything in that equation is known except for the current, and we can solve for it. We have the one equation. I is now going to be 10 divided by 2K, or 5 divided by 1,000, or 5 times 10 to the minus 3, or 5 milliamps flowing through that diode. And that may or may not be acceptable in terms of the magnitude, but typically you want that current to be limited. You don't want to hook a diode up to a battery without any kind of limiting resistor. This is critical. That 2K resistor is critical to try to keep the current flowing through that diode below a certain peak value. You may not want to make that or allow that current through the diode to get above 30 milliamps. If it does for any length of time, you're probably going to have to go back to the store and get another one, because this one will be burned up or burned down. What if we had a practical diode? That was the analysis performed with an ideal diode. What if we had, now instead of the ideal diode, suppose we had this practical diode. Instead of that IV curve being flat in the negative and straight up right at 0, now it's going to have this little knee in it, and it's going to have to be a little bit positive before current's going to be allowed to flow through that one-way valve. Or now our forward voltage across that diode is going to be 0.6 volts. And that's what can be called the diode forward voltage, or the forward voltage drop of that diode. It might be referred to as V sub F in some literature, for example. We've already performed the KVL with V as a variable. We can simply rewrite that. It was minus 10 volts. We're going through that source. Now we have the voltage dropped across the 2K resistor. And we also have our voltage dropped across the diode. I'm just curious where that went to. Do you recognize that? That's an I. I am afraid to erase it, so I'm just going to leave it. You can put that figure or variable in your paper and you're going to go, what was that? I don't have any idea what that is. That almost looks like a tire swing, doesn't it? If you were a young child, you now are in this tire swing, swinging back and forth. Sorry, that's an I. With this, and if V is now our forward voltage of a more practical diode of 0.6 volts, we can plug that in, and that now has not introduced any new variable. We're now allowed to solve, or we're now able to solve for that current I, which is now 10 minus 0.6 over 2K, which isn't much different than what we just had. Now we're dividing 2 into, or 2,000 into 9.4, or we now have, instead of the ideal diode saying that we would have a current of 5 milliamps, now with a more practical diode, it's reduced a little bit because of the forward voltage drop across that diode down to 4.7 milliamps. And that's maybe what you might expect, but with the ideal diode assumption, you're right in the ballpark. You calculated 5 milliamps, and that gives you then a feel for how how much current you're allowing to flow through that diode. I'm getting ahead of myself thinking, how bright is that LED or diode if it was replaced with an LED? So what if the diode was not just a diode, but we now allow it to be a light emitting diode or an LED? If we had, instead of just a one-way valve, we now had something that would illuminate when current flies through it or goes through it. Now our forward voltage for an LED is bigger than 0.6 volts. But that's really the only difference in the analysis. V, that forward voltage, is generally larger than the 0.6 volts that we had before for the practical diode. As one example, if we had a red LED, which is why you saw a lot of red LEDs, those were the easiest to build or sort of the first to come into existence, that might have a forward voltage around 2 volts. Let's just assume that that has a forward voltage of 1.8 volts. If that's the case, we still have the same governing Kvl equation. It's just that we have to replace the V with 1.8 where it was 0.6 before. Now we have I is equal to 10 minus 1.8 divided by the 2K ohm resistor, or this now becomes 8.2, or 4.1 milliamps in terms of current. And that makes sense. We're now not dropping as much voltage across that 2K resistor, and consequently we do not have as much current flowing through that series combination of current limiting resistor and LED. That may not be enough current to make that LED very bright. It may just kind of sit there and, is that on? Is it not on? You might want more current to be flowing through that LED than 4.1 milliamps to make it light up. But again, you don't want to put too much current through it or it will burn up and you won't see it light up at all after that. Suppose somebody wanted it to be a little bit brighter. Getting ready for Thursday, it's red and blue. I'm sorry, there is no class Thursday, right? Just to let you, that was the commercial, which we would have more commercial interruptions on Thursday. That's why we're not having class here. Let's suppose now you want 10 milliamps going through that LED and not the 4.1. And the reason that you might want more current flowing is to make that LED illuminate a little bit brighter. You're wanting to brighten that up. If that's the case, and if you remember the circuit, it wasn't very complicated, the circuit to turn on an LED, a source and a resistor. If that's the case, what can we change? Well, we have two things. We could change those two things. We could make the source, if we want more current to flow, and we have two things that we can change, the power supply or the resistor. Which way would you want to push the power supply if you now had the ability to modify that power supply? It was at 10 volts. You want to increase the power supply to get more current. That's one way to do it, but that may not be the most practical way. Maybe you don't want to go buy another battery or put another battery cell in series with what you have to try to get the voltage up. So if that's not the case, you can also change the value of the resistor. If we do that, then our KVL, let's say that we now do this one, that we decide to change the second possibility, which is the resistor value. Our KVL equation says that we still have the minus 10 volt source plus R times I. Now R we do not know, plus our forward voltage drop across the diode. Some of these things we know. We know now what we want I to be. Now we're saying we want that to be 10 milliamps. We also know what the forward voltage drop across the diode is. That's the 1.8. We haven't changed the LED. We're still using the same LED. We now have minus 10 plus R times 10 milliamps, which is 0.01, plus the forward voltage, which is 1.8. We're back to one equation. It's a different unknown, but now we can solve for that unknown, R. R is now 10 minus 1.8 divided by 0.01, or 100 times 8.2. Or now instead of a 2K ohm resistor, we could use an 820 ohm resistor to make that LED brighter than what it was with the 2K ohm resistor. Now you can go and get all of your resistors out that you carry around in your pocket, throw those down and start putting together different LED circuits with just a 9-volt battery, some resistors, and some LEDs. And it's not very difficult to create that particular system. What if you're creating those and you actually change things a little bit? Suppose that you are building up these circuits on your breadboard, so you don't have to solder anything or get too into it. What if the circuit is a little different? What if you now connect it in the following way? Suppose, and don't ask me why I turned it on its side. Now it's horizontal and the other was vertical. Is that the difference? That's not the main difference, although that's schematically maybe that makes it look different to you, but structurally it's a similar series combination of a resistor, a source, and a diode. Let's say this is a 1K ohm resistor. What do we know about that diode? Which end wants to be more positive than the other? The anode, which in this picture, is it right on the right side or the left side? The left side wants to be more positive to operate. I should have rephrased the question. In order to make that diode conduct, which way would you want to bias it? And by that I mean, how would you like to... I'm sorry, I'm cleaning up here. I'm seeing all these plastic pieces on the ground. I'm picking them up and throwing them away. I'm trying to have you think about which way you want to bias that diode to make it conduct in the forward direction. You want the anode to be more positive than the cathode, correct? And which end is the anode? It's the right side. So ideally, we would want the voltage to be dropped in that direction. We would want V to be positive in order for that diode to conduct. How we label that diode voltage is not that important. It's just we need to understand how we've labeled it, what that represents. In this case, if we had a V that's positive, then that diode should look like an ideal diode would just be a wire. It's a short circuit. So now we want to be asking ourselves, is it possible in this configuration for V to be positive? Or which way would you think that particular circuit is wanting to operate? If I said, analyze this circuit, what is there to analyze? What's given, what's unknown? What do you know in that circuit? You have a resistor, that's given, that's 1K. You have a source or a supply, that's given, that's 10K. You have a diode, which I haven't told you anything about it. Let's just assume it's ideal just to see if things will even work. So we'll assume it's an ideal diode. In order for it to conduct, you need its voltage across it to be positive from the anode to cathode. If you had to guess, would that diode in this configuration be conducting or not conducting? Not conducting, but it's not that critical. Let's just assume, though, to do the analysis, let's just assume one or the other. You've now, I think most of you said, I'm going to assume that's not going to conduct, so the diode would be off. Let's assume the diode is off. If the diode is off, what does that tell us about the current I? It's not going to happen, is it? The current in that direction is not going to happen if that diode is off. If the diode is off, what can we say about a Kvl relationship? How would we write the KVL equation using those variables that we now have identified in this circuit? If I start on the left, again, this is equivalent, and if you don't like the way that it's drawn, draw it in a way that makes you feel comfortable. If this makes you feel better, then draw it that way. If that makes you feel more comfortable or confident in your ability to sketch this. Or if that's still not very comforting, you could even just say, well, that's the same point effectively. Now I have a loop. Now I have a mesh. Now I can write my KVL. And if I start at this particular point, I can walk my way around in a clockwise fashion. The current I is associated with the blue path, the red current I, and now my KVL equation says that I'm going to see minus 10 plus the drop across that resistor, and then I'm going in, the way that I've labeled that voltage V as minus V, and then I'm back to where I started. And if you get comfortable with that first sketch without the additional dashed information, that same KVL equation is true or exists. But with this, if I is equal to 0, if this is now in play, that's 0. We can solve for the voltage, which says that V is now equal to minus 10 volts. And does that verify our assumption or invalidate our assumption? It verifies it. It says indeed that V is less than 0, and that's what's required for that diode to be off. And so that's really what's going to happen in that particular circuit. We maybe just connected it wrong. We put the diode in backwards. And for that reason, nothing's going to happen. If that was an LED and we put it in backwards, as long as we didn't put too much voltage on the left-hand side, we wouldn't destroy it. It would just block current and nothing would happen. Question? With a diode off? Well, the purpose... Oh, I think you see them all the time. You just don't know it. What did I just put away? Well, maybe it's not. If you go to your car after class, before you get in, and you look through the window, what's going to happen? Right? Something's flashing, maybe. You have a security, some light that's flashing. It's going off and on. So they might tie a switch into this, and they might now turn it off for a while. Then they time it and they say turn on, turn off, turn on, turn off, turn on. And that would then be something that might not take a lot of current. 10 milliamps is not that much current, but yet it produces a decent light. And you're only doing it for a fraction of a second to let the guy know that your car is not to be messed with. Question?
Why not just disconnect the circuit?
Why not disconnect the circuit? Because I would get tired if I was sitting there. I'm sorry. But you as a designer would set it up to where it would time itself. You would build a timing circuit that would drive a switch that would allow that switch to either energize the battery or take the battery out of the circuit.
So, I mean, if it's just disconnected, then the diode it's not rejecting current and it's not doing anything.
Oh, so you're saying instead of doing this, why don't you just disconnect it? You may want to have this in a particular part. Basically, I created this just to illustrate that you can do your KVL and Ohm's law and determine what's going to happen in this circuit, which could be on the final. I could say, analyze this circuit and tell me what I is. And you should be able to do that by just applying KVL and what you know about ideal diodes. And now that you know that, you might say, well, what's the point of that circuit? Well, maybe there's not a lot to that particular circuit itself. But it might be that it's connected to some other section of a circuit, and sometimes you want it to conduct and sometimes you do not. And that's what we'll get into in a minute, I hope, or not in a minute, but later on we'll see how we can use these diode circuits to our advantage or to help us. Let's look at another type of diode which has a more interesting name than maybe LED and just a diode, and it's even more interesting to draw. Suppose that we now have a resistor which is limiting the current, and now instead of just the normal diode picture, I put some arms or some elbows on it. Now that sort of looks like a stick figure, but there's no head or feet on that. It's just a diode, but this is now a Zener diode, and it has a little bit more interesting properties associated with it. It now is designed to actually be operated in the reverse direction. This, if you didn't have, I was going to come down and cover up those elbows, but if you pretended this was a typical diode and V sub S was positive, you wouldn't expect that to be conducting, would you? But these diodes are typically labeled with a particular reverse voltage polarity of in this case 7.2 volts. This means if V sub S gets above 7.2 volts, that particular circuit is going to start conducting. Before that, it's not going to have anything happen. Let me say this is my current, I, and I can now sketch the current voltage relationship for this circuit. In this case, if V sub S is negative, so now I'm walking up and down my voltage axis from left to right, and if I start right at the origin, and if I'm starting at the origin and I start walking to the left, I'm becoming more negative. If I become more negative as V sub S, that's effectively, do you see that that's sort of making this side more positive than that side of your circuit? If V sub S is big negative, then effectively that's like forward biasing this diode in the normal direction. The top is more negative than the bottom. In this case, it looks more like a conventional diode. It starts conducting at 0.6 volts. And it starts supporting a current. So this is where you might think of a forward bias diode is what's happening there. If we now walk in the other direction on the voltage axis, we're trying to find the current voltage relationship of this circuit. It's not going to conduct, and now this axis isn't necessarily drawn to scale, until we get above 7.2 volts, and then it's going to start conducting. And that's what these Zener diodes, essentially, an ideal diode, Zener diode, would look like. It would just turn on at 7.2 and support current in that. It would actually just sort of hold that voltage at 7.2 volts. Question? The 0.6 is coming from, if you think of, I'm wanting to use my hands. If you look at this particular diode, if you just had that diode in a circuit, it really doesn't matter whether the resistor is there or there, but if we now had something like this, we would have current going through that diode in this direction. And what would the voltage drop across a practical diode be? It would be 0.6. Meaning if V sub S is bigger in the negative sense than minus 0.6, so maybe I should have said that's a minus 0.6. I'm on the left side of the origin. That's a minus 0.6. This is essentially the circuit that I'm doing, and it doesn't really matter where my resistor is, whether it's, that's maybe how I should erase, is just go over and over. I think I would learn my lesson. That's now what you effectively have if V sub S is negative, is this red circuit. So this is like when V sub S is less than 0. In that sense, that Zener diode looks like a conventional diode in the forward bias direction. When you reverse bias that Zener diode, it actually now starts conducting at 7.2 volts, and that's what is happening on the right-hand side. Now we're allowing current to flow through that Zener diode, maybe not that much, but it now is allowing current to start to flow at that 7.2 volt mark. Question?
Is it actually like that from line through, or is it like the slope from the other drawings that we did?
The 7.2, it's going to be more of a linear than, it really depends on the Zener diode. So the question was, what's the line going to look like? And it's going to depend on the chemistry of your diode. Some you might want to be more sharp and have a sharper knee. Some might be somewhat flat, more like what this is. This next circuit that I am going to sketch, suppose that I put something like the following. Suppose I now put a couple of Zener diodes on top of each other. And suppose that these are ideal Zener diodes. What would you expect the IV curve to look like here's voltage and here's I, and let's say that these particular Zener diodes are 5 volt Zeners. If they're ideal, then we're assuming their forward voltage drop is 0 when they're conducting. When they're reversed biased, they will start to conduct at 5 volts, depending on which way. So this one is a positive negative. If we bias that one in that direction, it would start to conduct. And this one now is positive negative in that direction for the 5 volts. Suppose that this V is now let's say here's 5 and here's minus 5. What's going to happen with the IV relationship? Suppose I'm at 0 volts. What's going to happen in this circuit? If I am sitting right here, what's going to happen? Is current going to flow? No. Neither of those diodes are going to be forward biased. Suppose that I now make this V more positive than 5? The bottom Zener is wanting to just be stuck at 5 volts. If it's stuck at 5 volts and little v on the left is more than 5, what happens to that top diode? Is it forward or reverse biased? Is the anode more positive than the cathode? If little v is 6 and if little v is plus 6 volts, this point right there is now 6 volts. And this point right here is 5. Because this guy is, it's reversed by, this one's reversed biased. This one is wanting to be forward biased in order to conduct. And if it's an ideal diode, it would be 0 if it's forward biased. It is forward biased because its anode is more positive than its cathode. If that's the case, it's going to want to go up like that. It's not going to do anything until it gets to 5. Now suppose V becomes negative. Nothing is going to happen until V becomes more negative than 5. When V becomes more negative than 5, then it's not going to be in this direction. Now we're going to want current going in that direction. The bottom diode will be forward biased, and we'll have a picture in terms of our current voltage relationship. It's going to look like that particular waveform.
Wouldn't it require extra voltage just because each one would have that voltage of 0.6?
So now, if these were, so the question was, wouldn't it require more voltage than 5 volts to make that happen? The answer practically is yes. I was just assuming an ideal diode. So I'm saying V is equal to 0. The forward voltage is 0. If that's the case, then I'm just saying, okay, it's going to conduct at 5 volts. If they were more practical, typical diodes, it might take 0.6 volts to conduct, and then those 5 and minus 5 would be shifted to 5.6 and minus 5.6 would be the change. Let's do some load line analysis. Did everybody build a solar oven in Engineering 102? That's what we're doing now, sort of. That's how we're solving this. Do you remember how you figured out your temperature of your oven? It was this intersecting of 2 lines. That's what we're doing now. Maybe we don't quite know. This diode is a nonlinear device. And because of that, we can't just rely on our conventional linear analysis that we've been doing. Suppose that we start with the following circuit. Here's our battery or supply. Here's our resistor. And there's our diode. Let's say that this is now V sub SS. This is R. Here's our diode voltage, plus to minus from anode to cathode. And there's our current that could or might flow through that diode. This is actually, let's just look at a particular example that you can go back to if you want to. Let's just look at exercise 10.3 and part A. In part A, they give us a couple of specific numbers. They say, suppose that V sub S is 2 volts, and suppose that your resistor R is 100 ohms. And what they also tell us is that the current voltage relationship of the diode is given by figure 10.8, which is this figure. That's the figure, that's the current voltage relationship of your diode. That's figure 10.8 in the 4th edition of Hambley. That's what current will flow given a particular voltage across that diode. Meaning, if for whatever reason we had 0.8 volts dropped across that diode, then that would say that, oh, we should be having about 3 milliamps of current flowing through it. If we had 1 volt dropped across that diode, then maybe we would have more like 7 milliamps of current flowing through. And that's not a linear relationship between the current and the voltage. But we don't yet know how much current or voltage we're going to have passed or dropped on that diode or with that diode. That's going to depend on how we've biased or set this circuit up, and we've been told that the battery is now a 2-volt battery and the resistor R is 100 ohms. We want to now know what is the voltage dropped across that diode and what's the current flowing through that diode. What we want to do is, well, this we can think of in terms of its analysis. We could write a Kvl equation. Kvl is true. It just may fluctuate in terms of the resulting numbers based on what V sub D is. But the relationship is still true. So let's now do a load line analysis, is what it's called. We have the characteristic of the diode. That's this nonlinear curve. Let's now find another curve to see if it will intersect with this nonlinear curve. The linear curve, or the other curve, will be linear, and it's based on the Kvl equation. We have minus V sub SS plus R times I sub D plus V sub D is equal to 0. What we don't know, though, in this equation is maybe we do know V sub SS, we were given that, and we know R. What we don't know is I sub D and V sub D. So now we need to figure out what value satisfies both this equation and this picture. So we're going to now try to find an equation or another line that will hopefully intersect with this line, and the intersecting point is going to give us the sweet spot, or where the current and voltage of that diode will be operating when this combination of KVL and this current voltage relationship is both, or they're both true at the same time. Is that clear? If that's the case, we can now solve this for one of those unknown quantities. Let's solve that for I sub D. If we solve this for I sub D, we now have, let's say, isolated I sub D on the left and moved all the other terms onto the right-hand side and divided both sides by R. We now have minus 1 over R times V sub D plus 1 over R times V sub SS. What we don't know, or what we're treating as sort of our variables, are these two, the current through the diode and the voltage dropped across the diode. But in terms of those two parameters, this looks like a straight line. where V sub D is our x, I sub D could be y. This is now a straight line. What's the far term if that's a straight line? That's our initial point, or that could be our y-intercept, right? If V sub D is like x and I sub D is like y, this is y is equal to mx plus b. The slope is negative, and we have a positive y-intercept. And if you think in those terms, that's now this line going from left to right, maybe from higher to lower, and hopefully that will now intersect this exponentially growing current voltage curve on our diode plot, on that characteristic. Well, how do we sketch a straight line on top of that diode plot? If you go back to your experience with straight lines, how can you sketch a straight line? Find a point, right? Find another point. So we find 2 points and connect those, and we're done. What are a couple easy places to find points? One would be when I sub D is 0, and another one might be when V sub D is 0. Those are two variables that we don't know. Let's pick one, solve for the other, and set the other one to 0 and solve for the other, and that will give us our 2 points. Now we can connect those 2 points and make the load line sketch. Meaning, let's say at I sub D equal to 0, that now implies that we have 0 is equal to minus 1 over R V sub D plus 1 over R V sub SS. The R is just a number. We can multiply both sides through by R and solve for V sub D. And hopefully it's clear that V sub D, when the current through that diode, if it was restricted to be 0, the voltage dropped across that diode would be the entire source voltage V sub SS. That's all that's saying. That may not be happening, but that at least gives us a point on that. If we know that our circuit has to behave or satisfy this straight line, and it also has to satisfy this exponential shape, we want to know at what point does it satisfy both. But in order to do that, we're just trying to find a way of sketching that straight line to give us our second equation. We've now found one relationship that is going to be true on that. There's 1 point. V sub D is equal to V sub SS, and I sub D is 0. There's our point. Another point we could say is, well, that was pretty easy. Let's just set V sub D equal to 0. If V sub D is set equal to 0, well, that is pretty easy also. That says now that our diode current is just V sub SS over R. In terms of what we were given, so here's our second equation. Weren't we told what V sub SS was and what R was? So now we know that I sub D is equal to 0 corresponds to V sub D equal to VSS, which was 2 volts. That's one of our points. We were also told, well, we were told the same information. So when V sub D is equal to 0, I sub D becomes 2 over 100. Or 20 milliamps. And that's now 0.2. Which, if we go back here, what did I just say? We had 20 milliamps and 0 for V sub D. Maybe I shouldn't have been doing this in blue. Let me make this, I'm not sure black's the best color either. What was our other point? 2. I should have brought a ruler. it was 2 when I sub d was 0. Now I need to connect those 2 points, which isn't going to happen very effectively. That's supposed to be a straight line. Use your imagination. Wow, that's pretty bad.
There might be a tool that makes a line.
Oh, I'm sure there is a tool that makes a line.
It's at the bottom.
You think I'm going to experiment with that? You're crazy. Not with the luck that I've had. You'll just have to use your imagination and make a better line. You can, actually, I should have done the drafting trick. Let's see if this will help. So let me, not the, see? Luckily the blue won't erase. But what do? You set your paper so that the line that you want to draw is horizontal. Now I just need a ruler. But if I do this, is that a little better? Not much. Oh well, humor me. And this should be intersecting at about that point. That's the sweet spot. In terms of, that now tells us where we will be operating. Our operating point, whoops, using this load line analysis technique says that we now have a V sub D, I sub D combination. Uh-oh. Those aren't phasors. That's a bar. Now I don't know what to do with that bar. So we'll make it a tilde. That's our operating point. V sub D is now 1.1 volts, and I sub D is 9 milliamps. That's our operating point. And that's what would happen in that particular circuit. We now have a simultaneous solution of that straight line which was governed by the Kvl equation and the natural or physical characteristic of the diode. It has a particular IV characteristic. Meaning if I now give you a nonlinear IV diode curve on the final and I put it in a circuit, you should be able to do this. Sketch a straight line and find the operating point and tell me where that particular circuit is going to operate.
Could you also find the equation of the physical characteristics, like the exponential?
So the question was, could you find that diode IV curves equation? And you could, and then you could try to iteratively or via some other way find the solution of that curve and the linear curve. That would be another way of solving that. This is just a more intuitive graphical approach to that problem.
So it's okay to do like an inexact graphical?
Yes, it's okay to do an inexact graphical. This will give you a pretty good ballpark feel for where that current voltage is going to be in that circuit that is provided or given. Let's look at how else I could change that up on the final. Suppose I gave you the following. Suppose I said, okay, here's a circuit. And I say, analyze this. And you'd say, okay, give me some more numbers or give me some more parameters, but what might be your thought process? This is hard. How are you going to make it easier? How are you going to make your life easier? Instead of getting sick or getting too nervous about this particular circuit, what is an approach that you might think about doing? You might say, well, how can I make this look like what he did in class? If I could somehow get rid of what's to the left of those two nodes, what if I do this? If I label that A and B, is that suggesting anything? Thevenin. So now if you replace this with a Thevenin equivalent, then what have you done? You've now eliminated those dependent sources and resistor combinations. Now between A and B, you have something that looks like that circuit that we just analyzed. A source and a resistor. Questions on that? So if you're given something that looks more complicated, you can say, oh, maybe I can replace what's on the left of the diode with an equivalent circuit. And if I can do that, then I can analyze the circuit based on what you've just learned. Let's look at another way that we can use these diodes. Suppose we wanted to build a rectifier. And this is in section 6 of chapter 10. Suppose that you now have this oscillating source, V sub S. By that I mean it's alternating plus and minus. You put a diode in that circuit, a capacitor, and now you attach that to some load. And we may assume that that's going to be more like a resistive load. This is going to have some capacitor or some capacitance, C. The load will have a voltage drop across it, and it will probably be requiring some current to flow, I sub L. And let's say that this is now an ideal diode. If I now want to get some feel for what's going on, if V sub S suppose V sub S of T looks like that. What's going to happen as that waveform gets applied to that diode? If it's an ideal diode, what are you going to start seeing to the right of that diode as far as V sub L might be concerned? So if we simply so if, boy, I want to cover that up. I covered it up, could you tell? So if you virtually cover up with your hand the capacitor and the load, or if you just remove the capacitor for now, let's just say you remove the capacitor, then if that's a resistor in that load box, what you would see, if it's an ideal diode, would be this blue line. It would conduct only when V sub S was positive. It would shut off when V sub S was negative across that diode. With that capacitor in there, what's it going to do? Well, you're going to try to charge that capacitor up, and then it's going to hold on to that charge when things start decreasing. Then it's going to go up, and then it'll go down, and it'll go up, and it'll go down, and eventually what you're going to have is this voltage across that load, let's say in steady state, looking more like, what's it doing? It's just barely oscillating around that peak and low point on that diagram, where we might say this is V sub load. Our load voltage averages out to that dashed black line. That's the steady state, and we might consider this particular ripple, or the difference between the peak and the valley, to be our voltage ripple, or the change in voltage delta V. We want to now figure out what the relationship is between that small oscillation. Ideally, we would like V sub L to just be flat. We've now rectified this AC waveform, and we're trying to maintain that positive voltage with the charged capacitor. That's what we're trying to do. And we're trying to keep that up as best we can. And now it is ideally going to just be slowly oscillating between the low point and the high point around V sub L. In terms of that capacitor,
Is V sub L going negative, or is that, I can't tell if that's its own axis or part of the...
this is a new axis. I don't know which color to make this. This is now a separate picture. This is now V sub L. So I simply said, let's wait a while until we reach steady state. And at steady state, V sub L is going to just be bouncing around this high and low. And the bouncing is going to be modeled by this delta in voltage, delta V. If you needed to now tell me how much charge is going to be removed from, and what else do we know? Well, we also know if this is a time-varying waveform, and we're in charge of what V sub S is, we know what that period is of that oscillating waveform. So we pick 2 points that are the same on that V sub S and measure the time difference between them, and that would give us our T. So that's now the distance between the first time that goes through 0 going positive and then the next time it goes through 0 going positive. That's our period of oscillation. That's capital T of V sub S of T. Relative to that picture, and what do we know about charge and capacitance and current? If I said, well, how do I want to say that? If I now have current flowing from this, or if that charge on the capacitor is supporting the current flowing through that load, I'm going to lose so much charge every time interval, capital T, or every period of time. I'm going to lose an amount of charge. Well, maybe I want to say delta Q is going to equal I sub L times T. I sub L is coulombs per time, coulombs per second. T is seconds. So if I take the current times the time, that's going to be the amount of charge I'm losing off of that capacitor. What else do we know? Well, the other part of that circuit is when we are charging that capacitor, and we know that relationship for a capacitor, Q is equal to CV. That leads to ice, doesn't it, if we differentiated that. But in this case, our delta Q is going to be C. We're not changing that, but we are changing our voltage. And what was our voltage change? We were representing that by V sub R. If these are going to be the same amount when we're discharging and charging, then those two right-hand sides need to be equal, or setting those equal to each other. If we know what current we want the load to support, I sub L, and we know our time interval, or our period, capital T, and we know how much we want our voltage to fluctuate, we can solve for the capacitor that will provide that relationship between those currents, time, and voltage. Or C is now equal to I sub L T over V sub R. And that's equation 1010, and you may need to use that in one of your homework problems. Now, a more interesting circuit, that was a rectifier, but it was actually a particular kind of rectifier. How much of this waveform was rectified or retained or kept? If you said, here's the first half, here's the second half, first half being positive, the second half being negative, how much of that waveform is being used? Half. So that's a half rectifier. You can create a different combination of diodes to actually make a full wave rectifier. And that would be in figure 1028, which really means that you now have something like that, and that might be easier for you to keep positive. And I'll have to leave that to you to figure out for the homework on Tuesday. Is it the wrong figure?